Well, it's about 8 o'clock, so welcome to another session of the BPHO Computational Challenge run by Dr. Andrew French. So this week it's waves and optics. Please don't get bogged down in all about waves and optics if you're not quite sure about the physics behind it. What you're trying to do is learn the sorts of things you can present and the graphs you can plot and sort of how to sort of illustrate a topic through a variety of activities. So get the overall picture, the big view, rather than sort of worry too much about the fine detail of this. If you've covered optics and waves, that's great. But if you haven't, don't worry about that. Just sort of see how it's produced, so it makes a sort of coherent hour's talk. Okay, and over to Dr. French.
All right, good evening, everybody. My name's Dr. French from Winchester College. Welcome to the BPHO Computational Challenge. First, before we start, can we have an enormous release of emojis from my amazing students? I think it's Sophie and Ben and anyone else who was running the session last week. Fantastic job. There we go. Good. Very well deserved. So I believe the Python code that they co-created with you guys will be released on the website fairly soon. So if you are new to this business, do have a look at that. So I think you were plotting some exponential decays with radioactivity, that kind of thing. So today we are moving to waves and optics. There we go. Fantastic. Good. I see lots of celebratory things coming up. Right, so I'm just going to move on to our little presentation. Hopefully that can still be seen. Can you just confirm whether that's back on my screen? I've not accidentally hit the stop sharing button.
Yeah, it's there.
Fantastic. So what we're going to do, we're going to have a look at some waves and optics things. Of course, this was very much the computational challenge last year, where we had some amazing entries. And I'll have a nod to some of the tasks that we did. So I thought we'll start off with I call this, when I teach, the mathematical anatomy of waves. So you've been hit by a few equations now. So we'll just take a little bit of time in sort of working our way through what that means. And then we'll get to the business of plotting some waves and optics things. So I kind of think that you want to start off with a sinusoid. All right, so we've got a kind of sinusoid here, or could be a cosinusoid. I think I've defined it as a cosinusoid. There we go. And there's something called the Fourier theorem. So all periodic disturbances, and I mean disturbances in quite a sort of general way. It could be an electrical field, like an electromagnetic wave, or a magnetic part. It could be a pressure wave, in air, for example, like a sound wave. It could be the disturbance in the sort of equilibrium distance between rocks in a seismic wave, a guitar string, a slinky, all sorts of things. So waves are kind of a much more interesting topic in some ways than others, because they apply to almost everything. But you're not talking about a kind of ball moving or a sort of, I suppose you can kind of think of a field like electromagnetism, but it's much more kind of a topic which blends together lots of things. And a nice little idea based on Mr. Fourier is that all kind of periodic disturbances, even the jiggity-jaggedy ones that you get if you put some play a guitar, and I'll show you one of those a bit later, you can imagine these as a sum of cosine or sine waves of different frequencies, amplitudes and phases, and that's a really powerful idea. And so when you meet this at school and you look at sinusoids, it sometimes might be hard to think, well, hang on a minute, sounds that we just produce on we listen to on the radio are not like these signals, but of course you can construct them from those things. So if you like, sines and cosines are the kind of letters of the alphabet, although perhaps we should be more like binary, really. Sort of we can construct any number from strings of noughts and ones. So we don't really have an alphabet of sinusoids, but we've got the structures there. So anyway, this is the mathematical anatomy of waves. So let's just look at the picture first. So we've got a sort of sinusoid or a cosinusoid phase shifted, and the blue ones are kind of snapshots. So this is versus distance. So a spatial wave is like a kind of photograph of a wave, and we'll plot one of these very shortly. It's the first thing you might want to do. And you can clearly see things like the wavelength between the peaks. And there's also an initial phase here, which I call phi. A bit later, you might, if the wave's moving at speed c, and a double-headed arrow is my kind of notation for that, you can see the red wave being a bit later. And that's spatially that travels distance delta x. So the time that corresponds to the red wave is delta x over c. So that's the time later. All right. So what you can do is you can do a bit of mathematical transformations, and you can say, well, if I take a cosine wave, and I'm going to use radians here. Okay, so 2 pi radians means one, complete oscillation in sort of like cosine angular space. And so how many 2 pi radians do we have? Well, that's going to be x divided by lambda, how many wavelengths. But we're going to shift that by how far it's moved, which is the speed times the time. So x minus ct, that's our kind of translation from left to right. That number of wavelengths is the number of 2 pi's. So that's how we map our cosine wave into something which is a wave function. Disturbance is a function of displacement and time. And then we might start off when time is 0 with a phase which is not 0. In other words, a cosine may not start at the top, or the sine may not start at 0. So we have a little phase shift here. And so this is kind of the general formula for the sort of the basic components of all traveling waves, in fact, all waves. And we can simplify this a little bit. So you'll see this notation all over the place. And if you haven't met it, this is what k and omega mean. So k is called the wave number, which is 2 pi over the wavelength. So if you have a look carefully at this formula, you've got 2 pi x over lambda, which we can simplify as kx, all right? Because, when we're in sort of math land, we want to have a minimum number of symbols that describe the situation we've got more accurately. And omega is 2 pi f, or 2 pi times the wave speed over lambda. And that gives you a nice relationship, which is omega is the wave speed times the wave number. That's known as the phase velocity. So there we go. This is the sort of mathematics of waves. And if I was teaching you this, we'd do sticking lots of numbers and get used to these things. But kx minus omega t minus phi, that whole thing is what we call the phase of the wave, where we are in the cosine. You can generalize this from 1 to, n dimensions, 2 or possibly 3. And you can use a dot product. So my k, my wave number, is actually called the wave vector. So it has magnitude of 2 pi over the wavelength. So the wavelength here will be, it's like looking down upon a wave, would be between the wave crests, but actually it points in the direction of travel. So a wave vector where the wave is moving. And if we dot that with the position, that's going to be the kind of spatial phase. So it's quite easy to generalize our picture to more complicated 2D things. And I'll show you a little simulation which is relatively hot off the electronic press. Anyway, so firstly, I'll gloss over that you can take a screenshot, or you can download this for the actual code here. But I'll sort of highlight the key bit. So this is how we would plot our basic anatomy of waves. So a wave, the blue one at time 0, the red one at time delta t, and then also the wave disturbance versus time. So this is another representation, which might be the sort of thing you see in an oscilloscope. And I've got some nice titles as well. So this is a wave, a sort of sound wave going at 340 meters per second. It's got a wavelength of 0.5 of a meter, and its amplitude is 1 in whatever unit I pick, which could be volts, for example. If this is really new to programming, what I'm going to do is the green stuff with a percentage sign means a commentary. So that's for your benefit. And so I'm defining things like the wavelength, the amplitude, the wave speed, the unit of frequency. And I do things like, well, what's going to be my sinusoid separation? So how many wavelengths is that? So that separation there is 1/8 of a wavelength. And I could vary that to make that bigger or smaller. And then I've got some things like the number of waves to plot, the number of data points for the graph, and indeed the line width. So it looks good on the screen. And then I can work out my derivations. So frequency is speed over wavelength. The period is 1 over frequency, and my time delay based on delta x and my wave speed. And I've got these linearly spaced arrays. So again, if you're new to this, I'll demonstrate what that is in a moment. And then we can work out y and for y versus x, and then my time dependence here as well. And all the rest of it is just the plot routines. So that kind of thing, whatever you use, Matplotlib, MATLAB, or whatever, is a really nice sort of first thing to do. So, and I think this is common to a lot of the sort of courses that we've got. So once you've got some sort of equation that describes some physics, the first thing you want to do is make a plotter. And you could easily do that in Excel, but it'd be nice to do it in code. If you want to aspire for a silver or a gold in the challenge, getting used to plotting things in a programming language of your choice is what we want. So there we go. So I'll just demonstrate that sort of plotting routine very quickly before we move on. So if I say, I don't know, x is going to be linspace, let's go from 0 to 10 meters and in 1,000 steps. All right. And if I go for x 1 to 10, you can see we've got sort of a progression there. Each of these is spaced by 0.01. All right, so I've actually got a vector, and you can actually double click on it, and it looks like an Excel sheet with 1,000 rows. Okay, so and then let's just say we've got, so what do we got? Our phase. So we've got, say, lambda. Let's go for, I don't know. Let's go for 1.23 meters. All right, so our phase is going to be 2 times pi times, let's go for x divided by lambda. All right, so I won't phase shift it. All right, and that's the phase. And then what we can do is we can do y equals, I don't know, cosine of the phase. And then we're going to plot that. And there we go. So we should have a nice sinusoid there. Obviously, we could add labels and all sorts of things. And so there we go. So we've got 10 meters worth of waves, and our wavelength is 1.23. So you can kind of see that there. So really easy to plot some waves. We'll come back to that in a bit. All right. So let's go and have a little look at maybe a demonstration for how we might turn that into an app. This is called a standing wave. Before we do that, though, are there any questions that have emerged from our first bit? I'll put back my plot on the screen. We all good?
Yeah, I think Sophie and Liam are answering them quite happily. They haven't left anything unanswered at the moment.
Fantastic.
You can see they're all typing away.
Very good. So what I'm going to do now is, so now we can plot a wave. I'm going to sort of show you how that can be put into an app. Now, in terms of programming sophistication, the making of apps, is not the sort of like the next thing you would do. You need to get quite familiar about writing some code, but it's really a worthwhile activity. So because you now are producing a human-computer interface. So let's go. So I've got all sorts of apps. By the way, you can get these if you want to download these. You'll be sort of stuck with the MATLAB environment, but I'm sure you could convert them. I'll just minimize that. So on my website here, that's the, just move out, this is Shams out the way. So this is the Eclecticon, eclecticon.info. And if you go to the programming page, so if I go here, for example, there's a course in coding. You can get stuff on Excel, on MATLAB, on Python. And if the MATLAB one, you can click on apps or code, and you'll get a sort of several 100 megabyte zip file, and you can download everything. It might not be the most up to date, because I tend to do that every sort of 6 months or so, but if something's not there that you've seen, I'm sure it will be updated soon. Okay, so everything you can see today, you can download for free. Right, so if I look at my apps, I've got lots of them. These are all the ones in the corner. And what we want is the standing waves, which, there we go, standing waves. It's got a very original name, as you can tell. And it looks like this. All right, so what's going on? So when you pluck a guitar string, and I quite like playing guitars, for those of you who know me, that's something I like to sort of perform with some physics stuff as well. Lots of physics songs. And so this is a snapshot of a wave. All right. So if I've got some buttons here, which I can press. So if I press this button here, that evolves that wave in time. All right. So you can see the wave. Now, this isn't the fundamental. It's what we call the first overtone, the harmonic number of 2. So let's go for the fundamental. So you can see for a wave on a guitar string, you've got to have nodes at either end. Okay, so that's kind of constrained by the guitar. Then if you can see my mug here, but here's a guitar, and we've got a note here, and we've got a note at this end when I play a guitar. There we go. So that's that sort of design of the guitar. Pinch has nodes here. So the most fundamental wave vibrates. And what you tend to see in exam questions is you see this sort of envelope of waves. And what that means is just the wave is displayed at various time intervals, which sort of represent one oscillation. So, and if you pluck a guitar, it vibrates so quickly that you can't really see the string moving unless you're kind of, playing a really thick bass string. So this we can evolve it with time. So you've got to see how many periods that I've got. There's a sort of period counter below. So that's 1.38 periods. So what I've also got are kind of three scopes: the red scope, the black scope, and the blue scope. And these are particular spatial parts of my wave. And what I'm doing there is I'm plotting how things vary with time. So what you can see is that they all kind of vary in phase with each other. Well, say in phase, depending which sides of a node. They're all within a node at the moment, so they are all in phase, but the amplitudes are different. So the black one is of larger amplitude than the blue one and the red one. And if I move them around like this, you can sort of see how the amplitudes get bigger or smaller. Okay, so this is a nice way of looking at standing waves. Mathematically, it's a product of a spatial wave and a time-dependent wave, and that's a nice thing to work out. But ultimately, it's a way of visualizing these with all the information you need, like the wave speed, etc., etc. So if I change that to 400 meters per second, you can say how everything now changes. We can also look at a harmonic number. So there's 3 nodes now. Let's go for 4 nodes, maybe go all the way up to 10 nodes. All right, and you can sort of see how those waves vary. There we go. So I fixed the thing at 10, but you could change that. You can also have it doesn't have to have nodes at both ends. So this is like a sort of open-ended tube. So this might be sort of like an organ pipe. Let's make the harmonic number a bit smaller. There you go. So you're driving it at this end. This might be air pressure, and then you've got atmospheric pressure at the other end. As long as we don't have any sort of end correction, which is actually, it's quite interesting. It's about 2/3 of the radius of a tube, where the node is not actually at the end of your organ pipe. It's a bit beyond, which is quite interesting. But there we go. It's the same kind of idea. So that's a nice way of visualizing waves. Remember, it's got a sort of time-dependent part as well as a spatial one. And you can see how the phase changes in sign as you go between the nodes. So you've got to be a bit careful when you're kind of answering exam questions on these about when you take things are in phase or not. They are all in phase, but when you need to kind of be within a node, because obviously you're flipping a sign going from here. So if I move the black one from here, you can see how it phase shifts. All right, there you go. All right. Okay, so there we go. That's quite nice. Any questions before I move on? Apart from I have a lot of icons on my screen. All right, okay.
You're working through them. Brilliant.
Right, so here we go. So there we are. And this is the end correction, which is quite cool. So I don't represent this in the simulation, but L plus roughly 2/3 of the radius of a circular pipe is a whole number of quarter wavelengths. And it's got to be a quarter wavelengths because you've got an antinode at one end. Let's just say that's pressure, and a node at the other end. So that's your kind of, and that's a quantization condition. So the quantum in quantum mechanics often starts from wave theory, where we are constraining the number of wavelengths by our guitar strings or the lengths of our tubes, etc. All right, so here we go. So this is another little app, and I might actually, what does that? I don't know if that plays anything. So I might record something for you. How about that? So what we've got here is we're going to record a waveform, and you can see the left and the right channel. So I think what I'll do, let's just do this live, shall we? This could go horribly wrong, but let's give it a go. All right. So I'm going to do this is one of the more sort of involved apps. It's called Sound Analyzer. There we are, and I'm going to record a little tiny message to you. So here we go. So 5, 4. British Physics Olympiad is obviously the best. British Physics Olympiad is obviously the best. There you go. So what we've got is I've recorded my little statement of intent there, and we've got left and right channels because I've got a stereo microphone. And you can see it's pretty much the same. If you want to do something funky with sound, like Queen or something like this, you could modulate, you could change with time between the left and the right, and you could get my voice to bounce from side to side, all that kind of stuff. And if you want to have more channels and more microphones, you can create some surround sound. And essentially what I'm doing is I'm recording the movement of my sort of microphone 44,000 times a second. Then what am I doing with this? Well, first, let's just have a look at the waveform. So if we sort of zoom in, I don't know, from say 1.5 seconds to, I don't know, 1.52 seconds. And what you can see is the actual waveform itself. So there is a kind of frequency to it. You can kind of see the gaps between the waves, but there's also lots of other stuff as well. And these are the harmonics. So there's a lovely video, which you might have seen by Dr. Mark Looney of Cardiff University. I think he won a competition for sort of physics enrichment many years ago on sort of the physics of rock guitar. It's brilliant. I use that many times a year. And he talks about the kind of harmonics and visualizing them for guitars. So what I've got here is a spectrograph. Now this uses a really nice technique called a Fourier transform. Essentially what it does is it samples your signal every 100 milliseconds. And then it works out the frequencies that are within that. And then it does that every 100 milliseconds and stacks that on a graph. So rather than 10 kilohertz, I mean, we can go up to ideally up to 44,000 hertz, really. You won't see very much there. But in our range of hearing, maybe let's go for 3,000 hertz. And I think probably a little bit less than that, actually. Let's go for 1,000 hertz. And what you can see is some large sort of ready splodges here, which is essentially the frequencies in my voice. And you can sort of see, so there's not much going on, and there's some frequencies. Maybe if I sing something, that might be a bit easier. See, my voice is in good order today. La, la. There we go. La. There we are. So almost an octave jump. And if I was making a kind of, I think it's Sing Star. Is that right? Is that one of the computer games where you can sing and it tells you how close you are to being in tune? So what I've done is I've just sung, I'm not even sure what that note is. It's about 250 hertz. That's, I don't know, slightly off an A. If someone's got perfect pitch, I'm very sorry. And then you can see double that, triple that. In fact, most of it's actually the, so that would be the second overtone of the fundamental. And I could probably go maybe up to 2,000 hertz to see how far I got. Oh, there we are. So we've got 1, 2, so we've got one fundamental and 1, 2, 3, 4, 5, maybe 6 harmonics. How about that? For the high one, la, we've got the high one, which you can see is double my original note, so maybe an octave up. And there we go, and it all gets a little bit raggedy beyond that. So there we go. So this is how we can kind of visualize sound. And if you're plotting frequency versus time, that's rather interesting, because you can sort of see how things go from high to low, all sorts of stuff. And the waveform itself gives you a kind of characteristic. So I've got some nice sort of pictures of my partner, who's a proper musician, making some noises. A couple of other things to note is that we're plotting the color scale here is a logarithmic scale. So decibels are used a lot in physics, and it's 10 log to the base 10 of the signal power. That defines decibels. All right, so and sometimes you sort of set the maximum to 0. That would be known as dBms if you were in a sort of the lingo. So there we go. These are in dBms. The largest amplitude in this sort of signal power is set at 0 in the log space, and then we're getting smaller than that. So when it gets kind of bluey, you know, we're talking about 60, 70 decibels less on this scale. All right, so so a little bit of a diversion, I suppose. This is quite good. So if you've not met this before, then I think this is quite revelatory in terms of the sort of physics of music. And so I guess we've known something about the maths of music since the time of Pythagoras, about 2,500 years ago. And the sort of idea of harmonious music, these are ratios. So a fifth, which is used in rock music these days, is a ratio of 3 to 2. And so that would be, you know, so if you play an A 440 hertz, then 1.5 times that would be its pairing to make a fifth. All right. And where my octave, which I was doing or attempting to do earlier, it's not there now, that's a frequency ratio of 2. So if you've got a kind of modern keyboard, rather than using these Pythagorean ratios, we want a whole scale, right? So going from C to C above with the sharps and flats. And it's 12 parts, and each one is basically the 12th root of 2 as a multiplier. It's about 5%, I think, something like this. So if you go from, say, for example, to an A to a B, and then sort of a B to a sort of B to a sort of C to a C sharp, etc., etc. Then you are multiplying by the 12th root of 2. So there we go. That's kind of fun, isn't it? Anyway, this is the lovely Lucinda playing a violin. She'll be playing lots of different instruments today. And so this is using my my sound analyzer to look at this. Now, when you bow a violin, right, you're constantly doing work against the strings. So you're constantly feeding energy in. So that's why you have that wonderful sustained sound. And you can see it's about, I think I've asked her to play an A, 440 hertz. So you can see, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, maybe 12 harmonics above that. Really, really uniform. But when you actually look at it, you can sort of see that 440 hertz. If you're clever, you can sort of work out the time between the peaks and divide that into 1, and that's about 440. But there's loads of other stuff going on. And these are the harmonics. And indeed, the sort of jaggedy shape gives the violin its kind of characteristic sound. So if you played that on a different instrument, like, for example, a guitar, it's still quite jaggedy, but it sounds different. So, and also the difference is seen in the spectrograph. So when you pluck a guitar string, the bottom string, the bottom E, carries on for 5 seconds or so, but the higher frequencies don't. And why is that? Because the string is moving, doing work against the air. So the higher frequencies drop off, and that gives their guitar its kind of plucked like sort of percussive quantity, or quality, should I say. If you're playing electric guitar, of course, you might boost those signals and have all sorts of other harmonics added. So this is the flute. Again, we were pushing energy in with your mouth, you're blowing it in, and it's a bit like the violin. But the waveform now is so much smoother. You're not getting all these extra harmonics, and so it's getting a bit more like a sinusoid. So we're playing the same note, the same basic frequency, but it's the harmonic component and the sort of shape of the waves which gives the music its kind of characteristic flavor. I don't know if that's the right word you'd use. Yeah. Right. So this is quite nice. This is a chromatic scale played on a piano. So in other words, we start for C, then we go to C sharp, then we go to B flat and B, blah, blah, blah. Okay. So those of you musicians, you will know that. Digitally plotting all the notes. And this is probably not a lovely scale. It's not like a jazz scale or a blues scale, or miss out some notes, but it's a chromatic one. So in the waveform, you can see well, it's probably not me playing this, hitting the notes, and then they decay in amplitude. And there we go. You might have a sort of exponential decay, potentially, the sort of thing you met last week. And so those are all our notes. You can see that the difference in frequency between these is the 12th root of 2. And so that is a power law, which you can now immediately see in the sort of curves of our spectrograph. So it's rather nice. So anything kind of waves related, you can analyze in a really good way using this technique. Okay, so I think before we move on to laser diffraction, do we have any questions about sound waves and frequency spectrographs and all that kind of stuff? No, are we still there? Am I still broadcasting okay?
Yep.
Fantastic. Right. So there we go. So again, sort of making yourself a spectrograph. I don't know, maybe, I don't know if any of the questions are like, how can I do this? I would probably download the code for this one because the technique involves something called a discrete Fourier transform. So the key mathematicians amongst you might want to have a look at that. And if you go onto my Eclecticon website under the maths notes, there's a kind of recipe of how to actually produce that. But if you download the code, you can have a go. All right, so we'll have a look at laser diffractions. This is a really cool photograph, which I think we took. So we've got a green laser and a red laser going through a diffraction grating, which is a series of lines sort of like etched into some plastic. And they might go from, say, 100 to maybe 600 lines per millimeter. So the spacing of the lines is only a few wavelengths of light. And this green light is about 450 to 500 nanometers, something like that. The red light's more like 600. And you can see we get this wonderful fan of beams. So this isn't photoshopped at all. This is live. And to get those kind of beams, so if you're doing this in your physics labs at school, I highly recommend getting a smoke machine, a little sort of glycerol, so you can steal one, or sorry, borrow one from the theatre. And then your lab A smells like a sweet shop, and C, you actually see the straight lines, which is sometimes more interesting than the spots that they form on the walls. So here we go. Here's a bit of maths that you might have seen. So what's happening is we've got our plane waves incident upon our grating. And if you look at just two of them, you've got some slits here. And the idea is that if those slits are really tiny, you get kind of spherical waves. And the pattern we always talk about is that if you're lots of wavelengths away from your slit, then the waves emanating from the bottom one, all right, travel d sine theta further than the waves from the top slit. And we're kind of assuming plane waves here. All right, so a long way away, the waves are in every direction are kind of looking like plane waves. All right. And if you do a bit of trigonometry, if the angle is theta, this angle here is theta, and if that's d, that's going to be d sine theta. So if that is a whole number of wavelengths, you get constructive interference. And this is called the far field diffraction pattern, which gives you spots on the wall. In fact, defines what these lines are because they're at different angles. They satisfy d sine theta is n lambda, or sine theta is n lambda on d, where n is an integer. So there we go, we get quantization again. So I've got a lap for this, and what you do is, in fact, let's just go and run it. So another really good example of, you've got an equation for your diffraction pattern, and how can I explore it? Well, I think it's quite a good idea to build a little app. So we'll go for, what is it, diffractor. And here you go. So, and this is rather nice because if let's just say we start with the two slits. I've got a little sort of a slider here so you can increase the number of slits. Let's go for two slits. Let's have the slit spacing to be 3 wavelengths. And let's set the slits to be really thin, so like 0.1 of a wavelength, something like that. So what you do is you have, there's your wavelengths, 650 nanometers, this is red light. The slit spacing is 3 wavelengths. The width of the slit is really tiny. I can make that even smaller, actually. And what we see is we see spots where, well, in this case, S sine theta equals n lambda. All right, so where inverse sine of a third, inverse sine of 2/3, and inverse sine of 1. So they are 90, and you've got their angles there. What's that about? 19.5 or something like that. Now, if we increase the number of slits, sorry, the slit spacing, if we make the slit spacing smaller, what you can find is that the spots get further apart. And if we make the slit spacing bigger, they get closer together. And there's an inverse relationship there, right? Because d sine theta is equal to n lambda. And that's really powerful because your diffraction pattern gets bigger where your slit spacing gets smaller. And then if you're, talking about things like molecules, then, you can get a diffraction pattern which you can sort of understand their structure, which is on the human scale, as long as you use the right kind of, X-rays or something like this. And you get some interesting stuff here. So if I make the slit wavelength a little bit bigger, what I see is a kind of envelope. So the spots at higher angles get depressed. And eventually you get sort of like an extra sort of peak. So you can get a sort of complicated pattern where high angle peaks go down and up, and sometimes you lose some peaks. So the sort of biggest structure on your diffraction pattern, remember this is angle here, so it's like our sort of fan of beams, actually results from the smallest structure, the width of your slit. Your slit spacing define where your maxima are. So there we go, we've seen that. And the number of slits will sharpen up your pattern. So if we go from a double slit to a sort of grating, what we do is we sharpen those peaks up. So your diffraction grating isn't rather sort of a diffuse set of peaks. They're really well defined, which is like this. So there we go. We can kind of explore all of this. In fact, I can make it decibels if you like, with an app which just tells you what you want. And you've got these sort of things like sliders where you can move things. So basically, you change a parameter using a slider. And that kind of gives you an idea of how the behavior of your graph moves. So if your graph has got 3 parameters, make some sliders to sort of see how it dances. And that gives you, I think, a real sense of insight. All right, let's just quit that for a moment and go back to our presentation. So there we go. Right, what else we got? There we are. Of course, you can actually plot it in 3D as well. I'll gloss over this. I think this is sort of this is something to look in slow time, but you're using a complex number representation to describe the wave amplitude at distance r from this. Actually, you know what? Let's. This is. I said I've made something new. If I just explore this just in a little bit of detail. So if we've got, say, actually, no, I'm not going to look at this one. Let's look at this new simulation. So this is something that you probably have looked at before. It's 2 wave sources, like, I don't know, 2 microphones or things like that, or possibly even a double slit. And it is under, what's it called? It's under code So this is quite new. Physics, waves, and I think it's under interference. There we go. Right, so if I run this, we'll see if this works. Here we are. So I hope that's coming out all right. It's rather psychedelic. But what we've got is two wave sources, and they are 3 wavelengths apart. There's one there and there's one there. Now, if you look carefully, the yellow lines, so I've got rings here, concentric rings, they're coming from the left one, and the white circles are coming from the right one. So kind of eyeball that. And what I've done is I've worked out where they cross. And I've got a little sort of spreadsheet. Where is it? There we go. So the wrong page. There we go. Let's go here and let's just load that up. So there should be a little PDF. There we are. So here we go. So this is what's happening, is that if you can think about the Cartesian equation of a circle, so x minus a all squared plus y squared, that's like using Pythagoras. That's the wavefronts from this one here, the sort of white ones. And x plus a all squared plus y squared is the other one. Now, what do they equal? Well, what's the radius? Well, it's a whole number of wavelengths plus the time the distance that it travels in t seconds if it's going at speed c. We're assuming it's the same kind of wave. We can work, and those form the concentric circles. So different numbers of n and m are the different circles here. And what you can do is you can work out when they are equal to each other. So literally just basically set those equal to each other, and you can work out where the magenta spots are. If you want to plot what's underneath, you have to use this, which I think realize I'm missing an I here. Whoops. So there should be a complex I, K, R1. And R1 and R2 are the distances from my source to wherever my X, Y are. So I might just do a very quick, cheeky updater there. Allow me to edit it. We'll see. Will it allow me to edit it? Yes, there we go. So this is a math type. There we go. Live. So you can see this is new. There we go. Let's put an I there. Let's put that back, and hopefully it hasn't destroyed it. Look at that. Lovely. Let's just go and save that. Whoops. Oops. Control Y. There you go. Live editing. I'll try not to do that too often. So if we go back to our little animation, well, say animation, it's static at the moment. So if I use the arrow keys, and you can't see my hand's here, and what I can do is I can change the spacing, which is quite psychedelic. There we are. And so the color here is the sort of disturbance. I'm plotting the real parts of the complex wave function. For those of you who are sort of spotting that. So that's now nearly 5 wavelengths apart. And if I use the up arrows, I can then evolve that in time, I think. Can I do that? No, I have to press T, that's it. There you go. So now you can sort of see it moving in time. So there we go. That's my kind of interference pattern from 2 waves. So that's a nice thing. So this isn't even a kind of graphical user interface. It's literally a graph, but has some key press issues. So inside, and I think what we might do might just a little delve into the MATLAB function. I'll show how I'm doing that. So this is if you're not quite ready to make a GUI yet, but you might want to sort of add some user interface. So what I do is I have what we call a global array. It's something that all sub-functions can tap into. It's like a kind of a data structure that all parts of my code can see. If you this line here creates the figure, and the figure, this is a MATLABism, but when you create a sort of plot area, it will have a property, and one of those properties is what happens when I hit a key. So when I hit a key on the keyboard, it will run this thing called key press. So that's a subroutine. So when I hit a key, this thing is run, and basically it says, all right, I'm going to get all the details about my plots, which is in this array D, and this bit of code here basically says, well, what's the current key for my figure? And if it's the left arrow, I'm going to increment my spacing by 5% of my wavelength. Right arrow, I make it larger, etc., etc. All right. So, and if I hit the P command, I will print a picture, something like that, and I get something that looks a bit like this. All right. So you know, it's you need to figure out what that is for the language of your choice. But adding some form of key control is a really fun thing to do. Okay, so let's go and have a little look at what's next. This is a nice little model. This was in the computational challenge for last year. In fact, why don't I actually go into that challenge to sort of show you what that was. So this was so when we release the challenge, I'm afraid that's top secret for the moment, but we're releasing it in March. You'll get a pack like this with lots of tasks and things, and then a small document which kind of summarizes it. This is all about waves and optics. And if I find the one that was this one here. So this was challenge number 3. And so this is all about the law of reflection. In fact, let's look at challenge number 4, I think, which is a bit more interesting. So this is how you would derive Snell's law. And so what you do is you pick a point here, all right? And then you go from A to B via this point S, which is x, distance x from our axis. And what you want to do is work out what that path is. Now, Fermat's principle says that the path that the light takes is the one of the least time, which is quite interesting. And this is how you work out the law of reflection. So you look at the path length to go from here to here. Actually, let's do this one because it's probably easier to understand. It's the same principle though. So you use some Pythagoras to work out how long it is from A to S to B. And what you do is you're saying, well, let's work it out in a medium as well, because it might be, that's your refractive index. And what you do is you plot that time versus X, and you get a kind of unhappy mathematician. And if you use some calculus or just by plotting it, you'll see that when X is half the distance, that's the minimum time to get from A to S to B. And that describes the law of reflection, because what you can do is that you can relate that in terms of angles. When it's in the middle, theta equals phi. So you can do the same thing. It's a bit more, you can do the maths of it if you wish. That's kind of obvious in the picture. You can do the same thing for this one. So I'll show you the picture and then I'll just illustrate the maths. So in the refraction case, the refractive indices are not the same. So the wave speed, C1 is the speed of light over N1, and the wave speed in this one is the speed of light over N2. And what you do is to work out the minimum time that goes from A to S to B. The constraint that produces that is that of Snell's law, which is quite nice. So that's a derivation of Snell's law if you've never seen it. But we want to plot that, of course. We want to plot the time of flight going from A to B as we vary X, and that's what the graph looks like. And it's not symmetric in this case. And when you work it out, the value of X, it allows you to work out theta and phi. And in fact, this is how you do it. So you write your time, you differentiate it with respect to X. That's called a partial differential. Basically means everything else is constant apart from X. And when you work it through and you've got some trigonometrical ratios here, you end up with Snell's law. So delta t by delta x is 0 when n1 sine theta is equal to n2 sine phi. So that's a nice little exercise, but it's even better if you can plot it. Okay, so we've got a few minutes left. So this was another thing from the challenge. So I think I'll go back to my my presentation now, which is this one. So there we go. There's reflection. There's refraction. Another thing, you probably looked at biconvex lenses in your physics classes, but you might not have seen it in this way. You've probably looked at this diagram where you've got some light rays going through a lens. And if they're parallel, an ideal biconvex lens will push it through a focus. It doesn't stop there, of course, just they pass through that point. And if you combine that with light going straight through the middle, that allows you to find out the image coordinate given the object coordinate. All right, so you've probably drawn this diagram loads of times in problems, etc. But you thought, well, can't we actually use that to work out where a sort of two-dimensional image might go? So this is one of the major kind of paradigm challenges in last year's piece, because it involves a bit more graphics than we've ever used before. So we had some amazing sort of like websites for people having dynamically moving images. So essentially, this is James Clerk Maxwell, and the spot on his forehead is XY. And if you apply the transformations, what you find out is that big Y is minus big X, Y over a little x. And this is the X coordinate. All right, so you can sort of do the mathematics of this. Well, that means you get your inverted image, but it means you can transform everything else. So I've got, as you can imagine, my bitmap here is a grid of pixels. X, Y, and I'm transforming them this way, and that's where they end up. So if you can move that around, maybe your mouse points, you can work out where the image is. So I think we'll do that. So here's a little bit of MATLAB code. So if I go to physics, I think it's under optics. There you go. We've got lenses. So we'll go for a converging thin lens. There we go. Let's have Sybil the cat. She's sadly no longer with us, but there we go. We can make her live again. So there we go. If I move Sybil the cat upwards, we've now got an inverted cat on the other side of the lens. There we can make Sybil smaller, or we can make Sybil larger. There we go. Isn't it? All right. And this simulation doesn't go within the focal range. I've got another one for that, which is my magnifying glass. So if we want to make the cat bigger, obviously, there you go. So here we are. So now the cat's inside the focal range. And now we've got diverging rays. So from the spot at the top of the cat goes through the middle, horizontally goes through the focus. And if our eye was roughly where my mouse pointer is, I'd be thinking at those straight line rays, where they're coming from. Well, I extrapolate with my dashed lines. I think they're coming from here, that green spot. So we do the same thing for every pixel of Sybil the cat, and we end up with an enormous beast, which are, well, I hope you like cats. Anyway, there we are. So, so that's the virtual image, the apparent source of light. So we can think about these things as a transformation, which I think is quite nice. So if we do that with a biconvex lens, let's just, there we go, there's my magnifying glass. What about a concave mirror? So we have this amazing experiment. Here we go. It used to be a flying cow. So you can see the inverted cow here hung from a retort stand. Then we've got the Ray Optics poster as well. And this is a spherical mirror. And I think this came from some sort of World War II searchlight. You know, we got some ancient kit in Winchester College. And it's brilliant. So we sort of like, I use this quite a lot. So but slightly strangely, we don't know what happened to the flying cow. The flying cow disappeared to pastures new. So now we have a flying dinosaur instead. So you hang the inverted dinosaur here. And what you do is if you stand in the right place, you will see. So there's, if you look carefully, there's the real dinosaur. And this sort of upright, enormous dinosaur seems to appear right in front of your eyes. And if you let it swing forwards and backwards, it looks quite good. So what's going on? Well, this is what's happening, is that, so we go back to Maxwell again. If we take a ray of light going through the middle of our spherical mirror here, it will just bounce back. And if we go horizontally, we can think about the radial of that spherical mirror going from the center of the circle. And the angle of incidence is the angle of reflection. So that ray bounces off here. Now, where those rays converge should be a real image. And indeed, that's what you see. So in a concave mirror, you get a real inverted image, not a virtual image, which I think adds to the sort of mystery of this. So I've got a little simulation of that, which we can run. So if I go up to mirrors, and we'll go to a concave mirror. Let's go for the dinosaur this time. Here you go. Here is a picture of the dinosaur. And there we go. So I can't really make my dinosaur much bigger, but if I sort of go towards it, you can kind of see it's getting bigger. There we go. Look at that. Anyway, so it's quite nice. So what we're doing is the sort of transformation of those points. And what we have to do is work out mathematically from X, Y here, what happens to big X, big Y here. And it's a little bit more involved because you've got to do some trigonometry, but it is doable. And that was in the challenge from last year, if you want to have a look at how that goes. If I've got that spelled out. Okay, so, and you can do a concave mirror as well, which is quite nice. I'll skip over that. Anyway, so lastly, this is even simpler. And this is a really nice little demonstration, particularly if you're lucky enough to have a kind of flatbed, sort of an iPad or something like that, some sort of inkable tablet. And what you do is you take a photograph and you fit it within a circle. And then you do a little mapping where the pixels of that grid your image find the radial grid of this sort of distorted image. We call it an anamorphic transformation. And it looks like this. So here we go. Here's a kind of a nice one. So what you've got is that depending on your sort of X and Y coordinate, you define it, you map those to an angle or a range. All right. So I'm basically mapping my cat into a kind of sector. You can kind of grid this. And I've set it to be a radial factor of 3 and 160 degrees. If you make it all 360, that looks quite cool. So that's a bit like this one. That's me with some sunglasses at Port Merion, and I'm sort of splurged around a circle here. All right, so that's something you can do quite easily in NumPy or MATLAB. Now, what's really amazing like this is if you get a sort of curtain pole. I've got a picture of it here. Here's a curtain pole made of metal. So please don't use your parents' curtain pole. You want to get a cheap one from a hardware store and polish it up. And then what you do is you sort of like pinch your graphic so the curtain pole just fits within the circle. And what's important here is that the curtain pole, all right, is around your image, but the center of your arc is at the bottom of your image, and that's quite subtle. All right, it's not the center of your curtain pole; it's where the red spot is. And what you do is you get what looks like a 3D image. So I got inspired by this, seeing one in the Science Museum. If you go there in London and go upstairs to the maths department, you'll see. Actually, I don't have a picture of it. Actually, I do. It's in the other one, I think. Let's just have a little look. I think it's in here, I hope. Anamorphic images. Do I have it? No. Oh, do I? No, I don't have it with me, I'm afraid. So the picture that's in the Science Museum is this amazing kind of medieval, well, it's a bit more than medieval, sort of like a 16th century ship. It's like this fantastical oil painting of a ship. And it's really distorted. It's sort of painted in this sort of weirdly curved thing. And in the center of it is a sort of salt cellar with this polished mirror. And if you look at the mirror, you see the ship as if it's sort of floating in 3D. So you can make these yourself. So that's a nice thing to do. Okay, so I think I might skip over that. So we've got one more, which is what we call the Doppler effect. This is a lovely sort of thing where you've got, a siren produced from a police car or ambulance, and it's coming towards you. It's high pitch and then decreases in pitch as it goes past. And this is a really nice demonstration from ophysics.com. I think, can I run this actually? Does this work? Oh yeah, that's cool. So what you can do is you can see your source moving, producing waves. And if I can I stop it? There you go. Right. So basically, what's happening is because you're it's moving away from you, what you'll see is the wavelength essentially kind of increases when it's going away, and when it's before it's coming towards you, the waves are kind of bunching up. So you see an increased frequency when it comes towards you, a decreased frequency when it goes away. And this is quite nice to model. Let's go back to that one. There we go. So this is the kind of geometry you can sort of see of my spot kind of coming past, producing waves. And this is sort of the idea of redshift and blue shift. So redshift is your wavelengths getting longer, which is like most of the galaxies in the universe as the universe expands, and blue shift is they're coming towards you. Some are doing that, of course. And so the first time I did this, I did it in Excel. It's a little bit tedious, but it can be done. So what you've got are lots of little wavefronts, lots of little circles. And essentially what you're doing is that as your source moves, your wavefronts have got a bit further, but of course where they are centered will change. So if you imagine a kind of an aircraft going along and dropping a stone in a pond as it goes. So once the aircraft's currently here, so it's not producing any waves. Delta T ago, it was there and produced that one, which is now evaluated this one. The sort of like red curve was produced at the origin. All right, so once my stone is now at 8 units along, the ripple it produced at time 0 is now the big red one. All right, and then you can visually see how the things are bunching up, which is quite nice. So there we go. So a wavefront radius increases as the initial position decreases, and also a shift of the wavefront center. So you can do this in Excel, or you can do it in coding. I'll just skip over the maths for the moment, which is this one. So this is the kind of idea, really. This is what I did in MATLAB. And what I've got is that this is the sort of where the center of my circles are. So the first one, the dark red circle, is here. That's where I was at that point when it was, the wave was created. The red one was created when I was there, etc. And the blue one, I'm right in this position. And if you work it through, what you can see is that the observed wavelength, so what you see here or here, divided by the emitted wavelength is 1 plus the ratio of your velocity to the wave speed times the cosine of the angle. What's the angle? Well, it's this one. So if in this case, theta is 0, so it's 1 plus u over w is that ratio. So you can kind of see that here. So there we are. Right, so that's the Doppler effect. And you might ask, well, what happens if I go faster than the wave speed? In this case, we get a Mark cone. So I think that O physics simulation is quite nice. You can actually demonstrate this. So if I go for my source velocity to be bigger than my sound speed, I wonder if I can do that. Can I do that? Speed of sound. Yes, here we go. Source velocity is bigger than the speed of sound. So if I start that now, what you'll see is it will produce a shockwave as it goes. That's quite nice, isn't it? So if we have a little look how that might be modeled. Where am I? I'm in one. Yep, that's it. So here we go. And what's really lovely about this is that this can be worked out, the shock front. So in other words, beyond this point, we haven't had any time for the waves to get there. So my source is moving this way. You can actually work it out with some really simple trigonometry. This is Ernst Mach, fantastic beard. And that's where we get the Mach number. So, Concorde went to about Mach 2. What does that mean? Well, if we think about a source of waves here, all right, and in t seconds, we're moving at speed u. So in t seconds, we've moved from there to there, all right? And now in t seconds, my wavefront is, assuming it's a spherical wave, or circular wavefront in this case, is gone to here. So my Mach cone is formed where my line is at a tangent to that, if you think about it, because I'm producing circles. So this dotted line here is always going to be a tangent to these circles. And what we've got is a right-angled triangle. So CT's this end, the opposite side, that's the hypotenuse. So UT sine beta is going to be CT. So we divide both sides by time, and we can work out beta as the inverse sine of the speed of waves divided by your speed, or the inverse sine of 1 over the Mach number. So if we were at Mach 2, that's inverse sine over half, which is 30 degrees, which is quite nice. So there we go. Right, before I've got one more thing to show you, and then we'll call it a day. So do we have any other questions that have emerged? Are we still there?
I think we're okay for the moment.
Fantastic. Right, so there we go. There's some nice ones. So this is a Mach 10, really fast. And that's why, unless you're right behind something going at Mach 10, you won't hear it. Because, of course, the shock front is very, very narrow. Whereas if you're going at Mach 1, you're breaking the sound barrier, then that, that line is 90 degrees. All right, so you're going to get sort of the sonic boom going in all directions. So there we go. There's a Doppler shift. That's just about subsonic, and that's now a Mach cone. And then maybe you could write some slick code where you can modify, a bit like in O physics, your relative wave speed to sound speed, and you can go from the Doppler shift to one of these. That might be a nice project to do. Right, so I'll finish off with something that's really cool. This is a duck. We met the duck, didn't we, in the special relativity course 2 weeks ago. And what's really amazing, I mean, as a physicist, we're looking at spotting patterns, all right? And personally, I like patterns that I can see in nature as well. And this is just beautiful because I was born on an island, so I was always on a ferry looking at waves. And it doesn't matter how fast you go or how big your object is, as long as they're kind of gravity-driven waves. In other words, that the wavelength is much, it's quite sort of, is not of comparable size to the depth of water and that kind of thing. What you find is that the angle of the waves your vessel produces is the same. So if you're an aircraft carrier, right, the one that's sadly heading to the Middle East at the moment, that angle is the same as a small boat, is the same as one that's produced by a duck, it's the same one that's produced by a cruise ship. Fantastic. So this was figured out by Lord Kelvin, 1824 to 1907. And apparently, I think the story goes is that they were on board his yacht because he was quite rich at this point, and they kind of did some physics. How fantastic is this? So it wasn't quite the same as this, but I was on holiday with Lucinda many years ago in Croatia, and yes, I geekily sat on a boat and worked this out. So there we go. Maybe you can too. So what is the Kelvin wedge? Well, it looks like this. And there we are. There's first Baron Kelvin, William Thompson. So amazingly, the Kelvin wedge is about 38.9 degrees. And that's the angle between this sort of triangular wake. And you can also work out the angle of the wavefronts as well, which is about 54.7 degrees. It's the inverse tan of root 2. And this one is 2 times the inverse tan of root 2 over 4. All right, fantastic. Notice this is nothing to do with gravity, nothing to do with the water speed, the water depth. It's amazing. So this will be the same everywhere. In a liquid, I don't know, what would be methane lake on Titan or something like this, you'd still see the Kelvin wedge if you had a kind of skiff moving across that at minus 200 degrees or something like this. So here's my duck. And again, there's quite a bit of maths involved. It's all in Science by Sim 2 if you want to have a look at it. But this is the picture that I've put in the book. So you can hear your wave vector that's here. There's your position to some point. And you do something called the surf riding condition. So basically you can sort of see, you project these waves. So as you're moving, you can kind of relate your wave vectors to it. It's quite a nice analysis. But eventually, what's rather surprising is that G doesn't involve. All right, whoops. And there you go. And a cool thing is you can actually work out the wavelength that does relate to the speed of the object. So if you have a static picture, like this is the Isle of Wight ferry, I think, you can actually, just from the measuring of the wavelengths, you can actually work out the speed of the object without having to even look at another picture. So there we go. Thanks very much. It's 9 o'clock now, so we'll finish. Waves are absolutely fantastic, and there's some rather cool stuff to do. So there we go. I hope that's given you some inspiration to do some coding. You can download all of this, of course. Recommended next steps would be pick a project that fits with where you are. If you're just starting out, maybe you can plot the anatomy of waves, the sine wave. If you kind of know how to do that, maybe some of the Doppler effect, the circles, or the interference pattern. If you're plotting circles, that'd be really cool. If you want to find a bit more of a challenge, maybe make an app. Maybe you could tackle the Kelvin wedge, but you'll probably want to look up the science first. Thank you very much. We'll see you, I think, for electromagnetism next week.
One question, do we have a break next week for half term?
That's a very good question. I think we do. I don't really want to put my diary up on the screen. Actually,
you need to check the email that was sent out today. It has all the dates and half-term breaks on that email. So if you go back and you read your email that I sent this afternoon, you know which days that you are having half-term break.
Brilliant. I need to do that too, clearly. So everyone, yes, do what we're told. Do what Mrs. Sham says. Yes. Yeah, we could probably start recording now, I think.